like lots of developers saying, "Hey, show me the code." But
Okay.
personally, I love architecture, and it's so important. And there's so many developers out there who simply don't have a lot of experience doing architecture for large scale systems.
Yeah, absolutely.
All right, so we are
Let me just get
live. So
started.
let's
Yeah.
go ahead and kick things off. 1 second. Let me begin recording. Hello, everyone, and welcome to the next session of Zymposium, where Cameron Smith is returning after a what, 3 week, 4 week
Yeah, I think we were both on. It must be
holiday?
at least four. Yeah.
Yes. Well, it's fantastic to have you back. And I know there's probably some folks who are new to this series who found out about Symposium and joined after our last few sessions together. So I think it might be great to catch folks up with what we've done so far, basically what open source project we're working on, which is Bio Roastery, not to steal your thunder, but Bio Roastery,
Yeah.
what the purpose of this open source project is, and what we've done to date. And then once we catch folks up, we can talk about what we're going to try to do in the scope of this session. Does that sound like a plan?
Yeah, that sounds perfect. Maybe in order
All
to
right.
do that, I can even go ahead and briefly at least share my screen
Yeah, that'd be
so that
great.
I can walk along with some of the what we've discussed as the
Yes.
background proven architecture here.
So tell us, what is the purpose of Bio Roastery? Why are
Right.
you starting
So
this open source project?
Right. So yeah, there are many certainly commercial grade players out there doing something which probably currently looks somewhat like what we see in the background architecture I proposed as a foil for us to discuss transforming it or what might be required to transform some components of it into WebAssembly based components. But the purpose of the platform is to help to sort of automate a number of features of computational biology. And so, in the domain specific sort of aspects of that, the simplest sort of model uh, I would I would suggest, for those who are obviously, many developers out there, is just that, we want to ingest some data, we want to execute some, workflows that either perform some transformation or probably more importantly some model training and evaluation, and then we want to be able to obviously persist some statistics or information from the process and push it up into something that can be examined in a user interface, and you have to sort of take as the context that I would say most of the people in the computational biology field would agree that most of the tools that people produce are libraries that sort of help you do bits and pieces of what you would integrate ideally into a systematic sort of workflow execution manually. But the goal
Yeah.
with BioRoastery is to be able to have an open source platform that someone could use to spin up, whether it's in a small biotech or pharmaceutical company, whether it's in an academic lab or even in the government, and have a system that they could use to actually provide services to people who are not as computationally oriented, as those who are writing the tools that kind of allow you to do bits and
That's
pieces
right.
of this manually, and to
And I
try to do that.
remember
Yeah, go
we
ahead.
we
Yeah.
talked about two different personas. One is that experimental biologist who knows the biology side of things very well, but they can't really program. And then another sort of persona is that research R&D type experimental biologist who is familiar with information technology. They can code. They're able to contribute Python libraries and input. They're able to use Python libraries. And sort of this platform being a way for those two groups to work together on something. The end goal being an experimental biologist can come sit down at their computer and then select a bunch of existing data sets, maybe upload their own data sets, and then create a workflow from like almost plugins or different components out there, and then hit run. and then end up getting back the results of executing this workflow over these potentially quite large data sets to do training and post processing, summarization, and so forth, and then being able to access those results in a very simple way that doesn't require any technical knowledge.
Right. And just to cap that off, the pieces that currently exist are sort of an open source instantiation of all of the sort of configuration you need to set up an Argo CD managed Kubernetes cluster upon which you can deploy at least this workflow execution engine or any of the other components together with one library that makes use of this component. But the goal is to discuss before I proceed further to build out all of these other bells and whistles, where can we insert or begin thinking about, where we could either obviate the need for or replace certain components with possibly with WebAssembly components using Golem as our sort
Yeah.
of WebAssembly based sort of tool for that interface. Yeah.
Yeah, that's right. And so essentially what we've been trying to do here is cover requirements and architecture in enough depth that we can both take a step back and say, well, we can go with a sort of tried and proven architecture like the one you see here, which involves using technologies that are, 10 years old, 10 years and plus. I would say many of these technologies are 10 plus years old. So using one of these really proven technologies and architectures, or maybe we want to see if there's a way to incorporate a sort of next generation platform for building distributed systems such as Golem. I mean, that's the one I'm familiar with the most. So that's the one I imagine you came to me thinking in mind
Absolutely.
we might take a look at. So yeah,
Absolutely.
Golem being this next generation type of platform for building highly reliable and scalable distributed systems. And I've had a chance to absorb requirements from this project over our past few sessions and get a little more familiar with the domain, as well as sort of why you chose some of these technology components. And I know at our last session, we had some homework. Both of us had some homework, some take home stuff that we needed to work on. And yours, I think, was aligned with drilling into some of the requirements and capabilities that we previously talked about and demystifying, confirming, or rejecting some of our hypotheses. And then mine was more, okay, given what I know about this system, let's take that download component and let's figure out, number one, is there a case for using something like Golem to build this? And number two, if there is a case, what would it look like? And what would be the benefits, the pros and cons to building something like this on Golem? So let's go ahead and I think dive into some of your homework and then we can take on mine.
Yeah, absolutely. And I'll try to keep mine relatively quick. So just to, one more piece of context. So, this probably isn't the most interesting, service to discuss, but it is up at the front of, sort of testing out the beginnings of a platform like this. And that is what we discussed is the
Yeah.
concept for a sort of data ingestion and possibly, coupled ETL service of some sort. And I just, pointed out sort of roughly what the parameters of the kinds of data that we would, be looking to download would be. And, there's a very wide range. And the reality is that this doesn't cover everything that's out there by any means. And it's, of course, always growing rapidly. But I suggested that somewhere in the neighborhood of, 1 gigabyte is sort of silly, but up to 100 terabytes would be useful. But I pulled out an example of sort of like just really quickly, concretely what an example of this would look like. And so, anyone can go to the NIH NCBI website, and this happens to be like a particular data set from a particular experiment, and it's only one component of it. But what's nice these days is almost all of this data does have a hosting on either in object storage, either both on AWS and GCP. So we can take as kind of our first goal, because that's a simple, API to deal with in terms of downloading and is becoming increasingly available, at least for data that's available from the sort of governmental databases. So this is just like a 50 gigabyte file, which falls sort of in
Yeah.
somewhere in the distribution of along within that range, and somewhere probably near the mean of that distribution, that I would expect to be something common to want to ingest. And so if we just like quickly run a couple of commands, we already know probably, or many people probably know what sort of the parameters would be from this API. But the point is, we can do some of the basic things that we would want to do, simply put, being able to relatively freely hit this API and download chunks of this data concurrently.
Yes.
And so the way I just tested briefly, this 50, if my baseline would kind of be to do this with a tool called Aria that will indeed use that feature, and this 50 gigabyte file was going to take about 15 minutes or something to download, so maybe like around 60 megabytes per second. Now this doesn't include anything that's actually validating, of course, what you're
Yeah.
getting, and after you do that. But this is just a good we could chunk out a piece of this file or something
Yeah.
and turn it into a test case or something like that. So that was, I just so that API, we probably don't need to even worry, but these are roughly like the limits we're going to find there. But the important thing is it will support taking advantage of concurrency, which I think is going to
That
be
is very important,
essential.
because that's
Yeah,
one of the things we wanted to figure out, is if it were possible to accelerate these downloads by doing them in parallel from different machines or different nodes.
absolutely. And so, yeah, that's really the only direct, update on that front. I would say is that, yes, good. We can make use of, some of these basic tools, and of course, we can pull out more examples if we need them.
And these numbers are good for us to keep in mind. You've got a 50 gigabyte file here, that first one, and then you've got a
Right.
light file that's like 24 gigabytes. So what we're seeing is, at least in these few examples, tens of gigabytes being
Yeah.
common, and we should think about that and try to optimize to be able to handle those types of loads.
Yeah. And this is like a 5-year-old data set. So this is a
Which
little
is
bit
why
in
it's
this.
so small.
Yeah, I was just saying, that mean probably is creeping up at least to a hundred or two, but these are still data sets that people are actively using to at least prototype things on. So
Okay.
it's very reasonable, yeah, for us to sort of take a look. And yeah, so I think like that gives us something from which we could begin to imagine both what eventual test cases would look
Yes.
like, and yeah, I don't know if yeah, there are a bunch of other pieces of follow up that we could discuss, but I wonder if you nicely sent me this I think
Yes.
sort of initial proposal. So
That's right.
maybe we should move
That's
on to discussing sort of what else we need to know, at least in order to better cinch down this and what you had in mind so far.
Yeah, yeah, that's right. So, as I was thinking about whether or not it even made sense to use a sort of next generation distributed systems platform like Golem, some of the requirements that I had in mind were the sort of ability to do this in a scalable fashion over not only lots of, or rather large data sets, but also many potential users of this system. So we're looking for something that's going to be scalable. It's going to be able to easily handle files that are tens of gigabytes or hundreds of gigabytes in size. And that's going to require, I think, a special way of handling it. If we want to make sure that we maximize performance, we're going to have to start taking advantage of parallel downloads and parallel processing and so on and so forth. And so that to me says distributed systems, right? We're actually building a distributed systems because of the size of the data sets that we're working with. And not only that, but reliability matters. And I had to think about this for a while before I came to the conclusion that yes, we actually do care about reliability. And the reason is not because we can't recompute our end product in a deterministic way, given failure of any part of our overall workflow, because obviously I think just for scientific purposes, it's important that we do have that ability to do deterministic reproductions. So it's
Absolutely.
not important for that reason. And honestly, it is important for like financial transaction processing. And what the reason why we want reliability in that case is because we can't afford uh, to have a double spend problem where we spend the same dollar twice. And so
Right.
it's important in that domain for an entirely different reason. The reason why reliability, I think, is important in this domain comes back to one of the requirements you said early on, which is we want to do this thing fast, right? Maybe it doesn't have to be the fastest in the world, but we don't want a workflow that takes 6 hours to run to have to be rerun 4 or 5 times because there was one transient node failure in a cluster of hundreds of different machines that are sort of servicing the workload across all of these people and all of these data sets. And that got me thinking, yeah, reliability, I really do think is important because we want these things to execute as quickly as possible. And we don't want to have to do completely redundant computation in the event of some sort of transient failure. And then another thing I was thinking about that is relevant in the case of Golem in particular is the fact that you want this platform to be extensible. And why is that a problem? Well, if it's extensible and if it's multi-user or multi-tenant or some combination of multi-user and multi-tenant, then you don't want a random bug from some developer out there, some sort of, Python developer who knows enough about experimental biology to contribute a plugin for this platform to end up being able to take down the entire cluster across all users, or even like in the ideal scenario, I as a user of this platform can run multiple workflows up to some specified limit of capacity. And if there is a bug that is triggered by one of my workflows, it shouldn't have any effect on other workflows. And furthermore, like if you really wanted to go all out, you would even say that maybe every single user of this platform can determine what plugins they use. And I should be able to use plugins that I trust. And I might have a higher risk tolerance than someone else, so I might choose to trust some plugin that someone else might not trust. And we don't want someone using sort of low trust plugins to compromise everyone's experience on the platform. And of course, when I was thinking through that line of reasoning, it's just one of the most compelling arguments for using a technology like WebAssembly. And that is because if we build a system using WebAssembly properly, then we can make it extensible, but we can also keep it secure. And we can allow people to extend their own workflows with untrusted plugins without having that impact the safety and security and trustability of everything else that everyone else on the platform is using. So I think I've talked myself into, and I'm biased, I will admit that, but I've talked myself into there being a fairly compelling case for developing this type of platform using a distributed systems platform like Golem, which is built on WASM. I think I could make that case. Now, whether or not I can convince you of that, that's a different matter, but I can at least make the case to myself that, yeah, this is something that actually does make quite a bit of sense.
Yeah, I think all those reasons are really spot on. And you know, the the lineage there, I think, tracks what I'm sure many others have also seen as a theme across many of the talks they might have seen you give, where you
Yes.
start out thinking you're going to do something simple. And really, if you pay attention very quickly, you end up realizing that, you really ought to do things well, if you
Yeah.
can, because
Yeah.
it doesn't take much before, yes, you could argue like well, we can ignore this thing or that thing, for the short term, and maybe we can get something. But the very simple example here is, okay, I brought a kind of a smaller data set as an example, 50 gigabytes. The minute you're at 1 terabytes or 2 terabytes, just from a cost perspective, you don't want people accidentally triggering this over and over and over again and failing and
Yes.
getting 80% of it and 20% of it and not being able to properly track that. And then, of course, this is the probably one of the simplest components in one of these
Yeah.
workflows.
Right.
Or, maybe it's not, but it sounds like the simplest in terms of its functionality. And so you can only imagine now propagating that sort of, those sorts of problems downstream. And so even though,
Yeah.
it might be hard for people to sort of walk up to the plate, say, oh, let's, really go down this avenue for something that sounds superficially this simple. I think the
Yeah.
minute you start thinking about plugging into the architecture, all those things come out. So I don't think you're going to have to do too much to convince me. I think, but on the other hand, I'll try to play a role that I'm not very good at, which is being a bit skeptical. But we'll see how
Yes.
it goes. Yeah. So
Yes, you can be devil's advocate.
yeah, a little bit at
All
least.
right,
Yeah.
let me go ahead and share what I came up with.
Sure.
And what I decided to do was simplify the problem in some respects, and but also look at other more complex aspects. And how I decided to simplify it was, if there was something that was super low risk that would just be pure boilerplate to show, I omitted it from the design.
Sure.
Okay, so I focused on some of the challenges involved in building a downloading component that can be parallel and can be guaranteed and highly reliable and all that stuff, while ignoring certain essential aspects of a production implementation. So let me tell you what I omitted, but I think that would be very straightforward and low risk to incorporate in here. What I omitted from this design is the fact that, first off, we should never have to download a data set and apply some sort of filtering and transformation if we've already done that before. Right? This system should be smart enough so that if we're just doing something that a different user on the system did with a public data set, then we just have the results right there and we use them. Okay, so I don't
Perfect.
think that is significantly complex. I think it's very straightforward and doesn't materially change the architecture here. So I omitted that. The other thing that I omitted is the fact that, when you're downloading stuff, you're filtering it and you're doing some sort of one-to-one transformation of this data that's streaming in. You also want to be writing the original data set somewhere on the side. And the reason for that is reproducibility. So we want to be able to reproduce. We said this early on, that we wanted to be able to reproduce anything, even if one of these government data sets were to be changed or corrupted. Hopefully, you would hope that no one ever changes a published data set, because it is going to impact the reproducibility that scientists are going to have to contend with. But nonetheless, I think we want to guarantee that we can push a button on this platform and get back the same results. And that means that, if data is hosted elsewhere, we need to copy that into our system just to make sure that we're always working on that same data set if someone tries to reproduce it later. And also, if we can't
Yes.
reproduce it later, so we can find out what's different. Why can't
Right.
we reproduce it? That should be traceable. So I
Yes.
omitted that. Why? Because it's relatively straightforward to take the architecture for this download component that I came up with and add a side channel that just funnels the information off to S3. So it doesn't
Sure.
materially change anything. But that said, I did want you to be aware that this is not what I would consider a production grade architecture for the problem we set out to solve, because it does omit those two aspects which are important for you to get right, I think, if you were to build this in production.
Yeah, perfect. Yeah. So obviously we want to have some kind of content addressable storage that's going to be tracking transformations and also, storing the raw data and yes, we will need that. Some of the workflow managers we're already using, of course, have those pieces. So let's talk about the other stuff. Yeah, absolutely.
Yes. Okay. So here are some givens. First off, we are going to, the input to this download process is going to be a URL that can be accessed via the HTTP protocol, which contains one of these large data sets. And you verified for us that these servers, which are serving these data sets, do in fact support the accept ranges header,
Yes.
which means for those of our viewers who are not familiar with the HTTP protocol, that just means that we can request a particular portion of this file to download. And given that these data sets are supposed to be immutable, we should be able to have two clients request two different portions of this file at the same time. And indeed, you verified that seems to be possible and seems to do what you would expect. So our requirements are we want to download this data set quickly and reliably for some definition of quick and reliable. The definition of reliable that I've chosen is basically that we will never attempt to re-download a portion of the data set that we've already downloaded. And regardless of sort of, because the type of platform that you're talking about building is not something you deploy on one machine, right? This is going to be deployed on, who knows? Yeah, it probably depends on grant money and lots of other things that I'm not privy to. But you're probably going to be deploying on 100 nodes, or maybe 1,000, or maybe 10. It's going to depend. And also maybe people would host this themselves and deploy it on their own infrastructure, but there's going to have to be a lot of sort of compute associated with this platform. And one of the interesting things that happens as you go from one machine to 100 machines or 1,000 machine is that failure goes from an infrequent occurrence that can mostly be ignored to something that happens all the time. And you just have to incorporate some sort of compensatory mechanism for dealing with these random failures. A node goes down, a pod's killed by Kubernetes, whatever happens, you've got to be aware that over 6 hours, which is what it could take to download a really massive data set and apply all these transformations and filtering and replicate and so forth, there could be a number of things that go wrong. And we don't want to have to do more computation than is necessary. And that's where I think a platform like Golem gives us a lot of stuff for free. Like if I were not
Absolutely.
using Golem to engineer this, I wouldn't even try for that definition of reliability. It's just too much work. And I would rather push the hard parts on the user. If something goes wrong, they can always retry. It might start from the very beginning. There might be lots of redundant downloads that happen. But still, it would help minimize the cost of building something that I know to work. So I would choose that. But when using a platform, a distributed systems platform like Golem, that's designed to make it really simple to get that level of reliability, it just seems like a no-brainer to me. Why wouldn't we use that? Okay, so download the data sets quickly and reliably. Then also something we talked about that I really ended up liking, especially in the context of WebAssembly, is this notion of the download component itself can, in a streaming fashion, apply filtering and mapping transformations. And the reason I like that so much goes back to what we were talking about last time, which is in our original conception of how this was going to work, we would download the entire data set and put that in S3. Then we would load it up again from S3 and we would filter it and maybe map it and do some other stuff. And that basically doubles our latency, our length of compute. Like if we're reading the same data set twice, when we can do it in a single pass, then obviously it's going to take twice as long, maybe not exactly twice as long, because S3 local to our compute might be much faster than the original download was. But nonetheless, worst case, it's going to be twice as slow. And why should we accept, 60 minutes when we can get it down to 30? Or 12 hours when we can get it down to 6 hours or whatever it might be. And architecturally, it doesn't really complicate things all that much to say, okay, you wanted to apply these different types of filters. We're just going to do that as we're downloading the original data. So we end up storing only a fraction of the original data set. And then filtering is not the only thing we can very cheaply do, I think. But if there's any sort of mapping transformations, sort of one-to-one transformations that you need to do on the original data set, it's very cheap to do that at the point of download. You've got so many bytes in memory, you filter that down to a fewer number of bytes, you apply whatever transformations you can do without having to do joins or other complicated operations, and then you store that filtered and mapped data set. And why I think this is a great fit for WebAssembly is because we can actually make filtering and mapping, we can make them dynamic. We can think about plugins, that this notion of a plugin, and a plugin could define what sort of mapping and filtering it wants to do. And we can, even though this could be a third-party plugin that's not baked into the platform, it's just written by a Python developer somewhere out there, we can make that extremely secure, and we can sandbox it. We can make sure it doesn't consume too much memory. We can make sure it doesn't take down concurrent workloads, etc. So it's highly extensible. Doing this in the context of WebAssembly, whether you're using Golem or not, gives us the ability to make it as extensible as we want while not compromising security and multi-tenancy and other properties that are important for a platform like this.
Yeah, another beautiful thing about this, as we sort of arrived at that conclusion through our discussion last time,
Yeah,
is that I see you've even mentioned there, obviously the scenario where these may be going on in different regions, and if we can take that 10 terabyte data set down to one, for example, just by doing this during the initial stream, and never, of course, we keep it for the reasons that you described, but maybe we only need one copy of that, and we don't need to be shuttling that thing around over our network, because it's not just that by the time we have one copy of it, it's free to move it all over the place. So I
that's
think
right.
having that one initial transformation that might be able to radically reduce the data set size, so that we're
That's
really
right.
just caching that big thing, is going to be really advantageous. Yeah, and I can think of one very specific application where I'm hoping that's going to work out just as we discussed it last time, and as you framed there. So I think that's great.
And you also mentioned early on that a lot of the types of analysis you want to do in computational biology are embarrassingly parallel, you said.
Yes,
So
yes,
I like that, because anything that is truly embarrassingly parallel, we can fuse into this initial download, right? At
yes.
virtually no cost. And if we are parallelizing this download for reasons of getting things done as quickly as possible, then it also parallelizes whatever sort of mapping we apply. So if we've got like a classification or a training problem that can easily be done in a embarrassingly parallel fashion, then we can incorporate that as part of the initial download. So what we're storing, in fact, could be classifications, or in the limit, or it could just be sort of, if we're building a model, then we're doing that incrementally and we're aggregating data at the end. But fundamentally, I think that that way of viewing this problem allows us to, it opens up the door to greatly reducing latency, because we have that data in memory, right? We just got it. We filtered it down. Let's do as much as we can while it's in memory, rather than just writing it out and reading it back in and doing it later. It just makes good sense, I would say, if our goal is
Yeah.
to minimize the latency of these workflows.
So just to very, very quickly connect one, the domain specific application I can immediately imagine should work here. And I believe it's how we arrived at the discussion last time, is that, the data I showed are, short reads from of genomic sequences from a given biological sample. And the first thing you need to do with that data is to map it to a location within a reference genome. And doing that for one read doesn't depend on how you do it for another read. So we ought to be
Wonderful.
able to have that at least be executed, during that process. So just to throw in a little bit of like how we could actually apply this, and I think
Yes.
that's I think that's was part of the discussion of how we arrived at it last time. There may be many other things, but that alone should reduce the data size that we then need to operate on for anything downstream, significantly, or at least get that piece done so we don't need to touch,
Yes.
that again. So anyway, that's one place. Probably there are more, but that's the good one. I think that would should immediately be testable.
Yes. So another thing that just occurred to me as you were saying that is, uh, in the context of WebAssembly has introduced the component model, which is supported by Golem. And one of the interesting things about the component model is that it allows components in different languages to interact with each other. So if you're building a platform like this, then what you really want to be able to say to developers is, hey, developer, you can build your plugin for this platform in your programming language of choice. You don't have to use Python. You could use Python, you could use C, you could use C++, you could use Rust, you could use R, use whatever you want, build your plugin, and it's going to work with all basically, all the other machinery in here, regardless of the languages that these things are written in. And that is something that um, is given to you uniquely in a lightweight form and just out of the box with the WebAssembly component model that could be useful here because you got Python, right? Plenty of Python in this space. I assume plenty of low-level C and C++ libraries that Python calls into, probably a bit of Rust out there as Rust continues to be used for data processing and analytics. There's got to be a bunch of stuff
And some
that
R,
is,
as you mentioned. And yeah, I'm sorry to interrupt, but this is a perfect example of why actually I think computational biology is an interesting domain application for the component model in particular, is because sometimes even if we don't trust or want to utilize another method, we don't want to have to, as I sort of suggested in the sort of heading for this series, is we don't want to have to rewrite that, but we want to try to at least, we may want to run that on our data just to check, because everyone else is going to ask, why didn't you run this thing or whatever, and
yes,
say, okay, can we wrap that up then in something where, if it works as a sort of function,
yes,
we can execute that in whatever language it's originally written in, but we don't necessarily beyond that either have to touch it or trust it,
yes.
not to destroy anything. So anyway, I think that again, I can immediately imagine a simple example where we could test such a thing, but I think that's going to become, one of the reasons why I said I was going to play the devil's advocate. I'm really sort of cheerleading, but
You're not.
anyway, but yeah, but I mean, it was why we ended up getting in touch in some ways, is because I could envision that this would help to solve this. One of the things that the component model could help to do is to solve this hyperpolyglot issue,
Yes,
without translating algorithms. Yeah.
that's right. All right, so let's dive into this diagram that I came up with and I'll walk you through it. Here's the basic idea. So on Golem, you have this notion of component, which is basically just a component of your overall application. And then a component is basically instantiated into a worker, and a worker is a running instance of a component. So basically, a component is to a worker what an executable is to a process, right? Executable is the exe file that you run, and then a process is a running instance of that that has all the code inside the executable, but it also has in-memory state and it's actively doing something. And in a similar fashion, the component is like your sort of cross-platform WebAssembly component that can run anywhere, any language, anywhere, any machine or device. And then the worker is an actual running instance of that component that has all this in-memory state and it's currently executing. So I chopped it up into two different components. And the first one is this download supervisor component. And even though I don't have a ton of experience architecting applications on Golem because Golem's so new, I still see this as an emerging useful pattern, which is this idea that you want something to supervise a workflow and to be the sort of single source of truth for things at the level of the entire workflow. And that's the idea behind the download supervisor component is there's a one-to-one mapping between every download and then instances or workers that are created from this component. So a user clicks a button to launch a workflow on a data set or on 10 data sets, whatever, and for every download, a download supervisor worker is created. And it's the job of that worker to supervise the entire download process. Okay, so the other component is what I've called a region component, and a region component is responsible for a certain range of data in the source data set. And currently, this is specified as bytes in the pseudocode and whatnot that I've written. I don't think that's exactly ideal because we would like these boundaries to be at some natural boundaries in the data set. But if we're ignoring the requirements of filtering and mapping, then it's certainly sufficient just to download a file quickly to use bytes. But I think ultimately that decision will have to be tweaked. There's going to have to be some overlap on these regions. And that overlap is going to be determined by basically the maximum amount of space that any region could want on either side to do sensible filtering and mapping. So anyway, we can deal with that later if we
Yeah,
have to. It's just one of those things that has to be figured out for the production version of this.
got it.
So the region component is instantiated into n workers per download supervisor worker. So the process you should be picturing in your mind is someone hits that execute workflow button. That ends up being translated probably by another component, if this were on Golem, into a series of downloads. One of those downloads ends up being translated into a download supervisor worker. That worker says, okay, my job is to download this data set. And so one of the first things that it does is figure out how many workers do I want to use in order to perform this download. It figures that out, and then it creates that many workers and gets them downloading their respective regions, as well as plugs in whatever sort of filtering and mapping they should be using as part of this workflow.
So region here refers to region within the given
the
data
file,
set.
yes.
Got it. Okay.
Yeah. And I know we talked briefly about cross cloud region feature set as well, right?
Yes.
You said something about that.
Yeah. Well, I was just saying, depending on how, as you mentioned, maybe you have, hundreds or thousands of nodes in your cluster.
Yes.
Sometimes at some point, you're eventually going to want, the outputs of the workflow possibly to be available in a few places and so forth.
Yes.
But initially for this type of work, you don't need any of that, So
Okay.
I was just clarifying though that,
yes.
Because when I first looked at this diagram, my mind went to that topic.
Okay. Yes.
So that's not relevant.
Apologies for co-opting Amazon.
I just wanted to say it in case anybody else might see it and have the same
yes.
Accidental trip of their brain outside of the actual scope of the problem at hand, in which this makes perfect sense. But I just wanted to, clarify that. Sure.
All right. So download supervisor component, it's instantiated once per dataset download. And the worker's job is to basically do this. So first off, it has to figure out what sort of parallelism it wants for the download, as well as the filtering and the minimal mapping compute that each region worker will do. And then what it does is it creates basically one promise per region. And it's a distributed promise, which is one of the things you can do on Golem. And this distributed promise can be completed by the region workers. And the reason why it's creating these promises is because ultimately this worker wants to know when the download is done. Why?
Right.
Because it's got to piece together. The file has been downloaded in potentially 1,000 different pieces, and it's got to write back to S3 a linear file with all these pieces in the correct order. And it might need to do other things as well, but it needs to know when it's done. And so what it does is it creates one of these distributed promises, one per region, and then it starts instantiating the region workers for each region, and it hands each one of them off. It says, you are responsible for this part of the file. And here's a promise that I want you to complete when you're done. So it just goes through all the regions and does that. That loop will be extraordinarily fast. That will spin up n different workers, each one concurrently downloading a different region of the file, concurrently filtering the data in that file, and concurrently mapping it.
Got it.
After the supervisor has done that, it just waits on all those promises to be completed. And by the way, I use promise here, but that's not to say this has to be done in JavaScript or TypeScript or anything like that, right? This is a language agnostic type of promise. It could be done in any language.
Right.
And then finally, once all of the regions have finished downloading, filtering, and mapping, then its job is to go through every region in order, retrieve its data, and write it to S3. And that's it. There's other things it could do, and you might want to do when you implement the production version. But for now, this is plenty enough, I think, to be interesting. I did some pseudocode, which I'll walk through if we have time at the end. But first, talk about the region component. The region component is, again, it's instantiated n times per supervisor worker. And what it does is basically downloads the region from the origin dataset, applies filtering, applies mapping operations, and then here's one decision I had to make, and I chose to make this decision because my goal is to minimize latency. I figure you're going to make enough trade-offs on your own when you're implementing this that you don't need me to make more trade-offs and increase latency. So my decisions have always been biased towards sort of theoretical optimum time for running one of these workflows on a large data set. And so what I'm going to say here is every region worker will hold data in memory and not write it out. Why? Because if it writes it out, it has to be read again. And I would rather it not have to be read again
Right.
because it's just going to be written out to the big
Yes.
file in S3 in a linear way. And realistically, I think this is actually possible. Consider that example of a 50 gigabyte data set. Let's say you have, let's say you have 100 workers created to deal with that. Then that's 500 megabytes per worker that is being kept in memory. And that's assuming you're not compressing it in some fashion. I don't know how well these data sets compress, but they could compress. Is 50 gigabytes already compressed?
I believe it is not actually. Let's see. They have they do have a gzipped version. It actually goes down in that particular data set. It looks like it goes down to even 11 gigabytes. So that's pretty decent. I don't know, factor of 5 or so. Yeah.
Right. So that brings it down to 100 megabytes per worker,
Yeah.
which is totally reasonable. Storing 100 megabytes in memory, it's no big deal. And keep in
Yeah.
mind, this is all going to be blown away the moment the download is finished. And
Right.
obviously, if we're downloading a 50 gigabyte file with 100 workers, each one of which only has to download 500 megabytes, then assuming there's not some sort of crazy IP restriction or whatever on the source server, then we're going to be able to download that file very, very quickly. Right? We can saturate local network connection, and it's probably run in a very horizontally scaled server, so they've got a ton of bandwidth they can throw at it. We can download that 50 gigabyte file very, very quickly. And then we hold that in memory. As soon as we're done downloading that last byte, we notify the supervisor worker that the region has been successfully downloaded. We do that by completing the promise. So we complete the promise and say, we're done with this region. And then the only job of this worker after that point is to supply the filtered map data to the supervisor whenever it requests it. And after that, the worker's done. Now in Golem, workers live forever. So there's no explicit end or termination or cleanup that has to happen. So basically, the worker just has to expose a function for retrieving that filtered map data, and then the supervisor will call it. And then some period of time after that call completes, then Golem will say, hey, I noticed that this worker's doesn't seem to be being used right now. So it unloads it from memory and it stops consuming any resources. But even though it unloads it from memory, it still sort of has a copy and can recreate its state in case that worker is ever called again. Now, one of the things that we get from Golem is free reliability. So what does that mean here? It means that there's no way, take a look at the pseudocode here for the supervisor component. Basically, we get the total size, we determine some parallelism, we compute the region size, then we just go through this simple, dumb looking for loop. If you were building this on a different system, legacy system, you would have to worry about what happens if, like, we go through a few of these regions and then the node executing the supervisor goes down, right? Then we have to deal with cleaning up the mess we made and trying again or something like that. We don't have to think about that with Golem because it doesn't matter if a node goes down. The computation is just resumed where it left off on a new node, and Golem handles that. We don't need to think about that. We can really think about we're programming uh, on an invincible computer. Our code is executed transactionally. So we don't have to think about reliability concerns. And so here we're awaiting all of these different promises. There's no possibility that one of the region workers dies. Why? Because Golem guarantees 100% reliable communication between workers. So if there is a problem with some node, the worker comes back on a new machine, keeps executing from where it left off. We don't even see it. It's not even possible to detect that in our code. So we don't have to think about that. So we just write this dumb for loop. We wait for all these regions to do their downloads, their filtering, and their maps. And then we just, in a dumb fashion, we call for every region, we call this accessor function to get back that data, and we write it out in order to S3 and we close it, and that's it. And it doesn't matter what happens to the infrastructure. There could be terrible things happening with the infrastructure, and we can just ignore that and rely on this being executed with exactly once semantics.
Can
So
I
that's
just
a
ask a
great
question
simplification. Yeah, go ahead.
about how that works, how this magic works mechanistically? So I'm curious um, if a worker has whatever, 70 megabytes or even 100 megabytes in memory and it dies, when
Yes.
when the next worker is brought back up, how does it restore that state? So that it can continue without re-downloading, or does it?
It
Yeah,
does. It
yeah,
restores its state. So it continues from the moment it left off. And from the supervisor worker's perspective, it's like it never went down. Right? It can't
right,
tell that there was ever a problem with the machine.
right.
So how that works is right now we've implemented sort of replay semantics for worker recovery. And then privately, we've also implemented snapshot semantics for worker recovery, which is not quite polished enough to ship. So
I
that's why
see.
that's private, but it's an
Yeah,
experiment proof of concept. So I would say right now, what happens is as that worker is running, every time it calls out to the external world, that goes into a database log, a database like commit log. And that log is replicated to multiple machines. So it's redundant, it's fault tolerant, and whatnot. So in the event, and this is all happening in real time, in the event that that node goes down, then what happens is Golem detects that failure event. It creates a new worker on a new machine that is triggered in the same way the original worker was, with the same parameters and same everything. And then as that worker interacts with the outside world, we play back what the real worker's response was for every interaction. And because of the deterministic nature of WASM, this will result in that worker basically recreating its state to the exact moment before the failure event happened. And then snapshotting works in slightly different way. Snapshotting works in the following way. Basically, if the worker is at rest and not doing active work now, then its memory can be just snapshotted, and that snapshot dumped out, and then the worker can be restored with that the contents of that linear memory at some point in the future. And in the future, we might have other ways of achieving these guarantees. Like, for example, we could have a very custom and durable executor for WebAssembly bytecode, if you will. We don't have that now. We achieve durability with both the the replay log, which we call an op log. It's basically a database commit log, similar to a database commit log, and then also linear memory snapshotting. And you don't need to worry about that. Basically, users of Golem don't need to worry about that. They can just focus on business logic.
Yeah. No, I think it's helpful though to slightly demystify the magic of
Yes.
how that works
Yes.
because otherwise, I mean, I guess the point is in the database that's storing the event log is obviously more efficiently located relative to where new workers would be created. So
That's
even
right.
if there is some if there well, I'm sure you can optimize things so that you maybe this is all happening through disk, but if there is any network transfer, it's going to be extremely efficient, nearby
That's
network
right.
transfer rather than, of course, pulling back from some server from who
That's
knows
right.
where. So that's fantastic. And then sorry, one other question, although I know
Yeah.
we're running out of time, is just in the last step here, is the data that's been downloaded by that given worker, is it streamed back through the supervisor, or is it somehow? I assume that's what's happening. Yeah.
So what we're doing is when
Yeah.
we call into this worker,
Right.
we're calling get filtered map data. This just looks like an ordinary function call to us, right?
Right.
Actually, there's maybe slightly different syntax, but what's happening behind the scenes
Sure.
is this becomes a remote procedure call basically to that worker. It's all typed, it's all
Got it.
typed. We don't have to think about that, but it's reliable communication. So it's literally as if we're going to that worker and making a procedure call and getting back the results.
Beautiful. I see. Thank you.
Yes, and that's also how basically this would work. Instantiate region worker when we call some method on that region
Ah,
or on that region worker to begin the computation.
right. Okay.
Oh, okay. And this is just pseudocode. Don't expect this to compile or anything, and the
Oh,
actual syntax
absolutely
is
not.
going to
No,
be
no, but
different. But
yeah, yeah,
the,
of
the
course.
basic idea is correct.
Yeah, yeah, of course. Don't worry.
Okay. And
I
then,
won't copy this into the
all right,
compiler.
fantastic.
Yeah. Sorry. Yeah.
So here, more pseudocode, just download the region, apply the filters, and this could be done using some sort of plugin framework that's very secure and sandboxed. And map the data. And here's also where you could consider like caching this map data as well, because there's no reason if someone takes the same data set and applies the same workflow, there's no reason to do that more than once. And then store the data in memory, resolve the promise, complete the promise basically, so the supervisor is notified, and then we just have this. This is how things get started basically. This is just pseudocode placeholders for all this. And then here's our function that exports the process data. And the supervisor calls this at the end to get that data. So there is more work to do here. And I think we have more to discuss, but we are out of time. So what I think we could do from here is if this seems really promising, and if you can see there being a lot of value in the benefits that a distributed systems platform like Golem provides, especially in the context of sort of durability, which gives us reliability and lets us not have to worry about some of the complex challenges of building distributed systems, and then also with the not just durability but the WebAssembly nature of Golem, which gives us some very strong guarantees around sandboxing and security and whatnot, extensibility. Then what I think we could do is we've done the download component. It seems promising, although maybe there's some stuff here that I'm not seeing that we should take a closer look at, but this seems promising. So if you take a look at this and you're like, whoa, I think we should think about number one, how do we reimagine the entire architecture using Golem and see what sorts of simplifications that could have. But then also number two, how do we incrementally introduce Golem into a project that's not currently using it? Then we could take a look at both of those. And I think that's at least another session or two if you have the interest and availability to do that.
Yeah, no, absolutely, John, and really appreciate you taking the time to think through the architecture for what superficially could look like a simple component, but once you flesh it out, it
There's
will
more
be
meat here.
simple. It will be
That's why
simple
you
to
came to me
use.
and you're like, "This is
Yeah,
too simple," and I'm like,
yeah,
"Well,
yeah,
there's
yeah.
a lot of meat here if you want to do this right and scalable and multi-tenant and
Yes,
secure. have it be fast, don't do redundant computation, make sure it's reducible, reproducible. Even think about extensibility, right? If you think about all these things, then there's actually a lot here. But also doing that work here, I think simplifies the amount of work that has to be done to complete the big picture architecture.
Yeah. So I think it'll be great to do both, to continue the exploratory discussion going back to how we can, from a big picture perspective, redesign the architecture, given that the components will be, able to take advantage of the features that you've
Yeah,
illustrated here with the download component so that we can see what this would look like as we would begin to swap out those components, while at the same time, excuse me, being as concrete as we can at this level of abstraction without having actually, gone through the full process. So I think, yeah, it'll be great to continue for a couple more sessions, and look forward to
that'd be
doing
great.
that, John.
And I look forward to that.